Okay, and we equate that to all of those raised to the 0 on the right-hand side. Again, going through each of the primary dimensions, we start with mass. And what we have on the left-hand side is a 1 plus an a, and on the right-hand side, that's a 0. So from that, we get a is minus 1. Looking at the length, again, we can't conclude anything. Let's move on to time. So from time, we get b equals minus 1. Plug a and b back into the length equation. We get c is minus 1. So coming back to our pi parameter up here, we can rewrite that. Pi 2 is, we have viscosity, and everything else is going to be in the denominator, and so they're all raised to the power 1. So we have rho vd in the denominator. And that is our second non-dimensional pi group through this process for a sphere. So looking at Buckingham pi, the next step is step 6, where we have to check the dimensions. So let's do that. So we find those are both dimensionless, which is good. That means that we did our work right. And what we can write is that pi 1 is going to be equal to some function of pi 2. And substituting in pi 1 and pi 2. So we get that for a relationship. And this functional form f, we don't know that yet. This is determined via experiment. Another thing that we can say here, looking at mu over rho vd, that is 1 over the Reynolds number. So that's a very common non-dimensional number that we use in fluid mechanics, where the Reynolds number equals rho vd over mu. So that's good. We get something popping out of there that we recognize. Another thing, rho v squared, that one, and then d squared, this is an area, or it's proportional to area, and this is related to dynamic pressure, which we saw when we looked at Bernoulli's. And so that is related to 1/2 rho v squared, and sometimes we give it the symbol Q infinity for dynamic pressure. So what we're seeing on the left-hand side is something with our drag force divided by Q infinity times some area. And that then is eventually moving in the direction of what we would call a drag coefficient. And that is something, so we could say CD is proportional to this. There's actually a factor, the factor of 1/2, that is missing from this form of the equation. But just by using dimensional analysis alone, a lot of information is coming out of this process. And so you can see the efficiency in the technique, and really the efficiency, I'll write it out in the next paragraph here, and then we'll discuss it. So what we have here is that by going through Buckingham pi, we've been able to show that CD, our drag coefficient, which we had as being proportional or related to force, rho v squared over d squared, or some area, was a function of 1 over Reynolds number. And so what that means is that this is the functional relationship that we're after. And in order to do the experiments then, all you need to do is you need to vary Reynolds number, And if we do 10 tests, you could have 10 velocities. And with that, you would get some sort of functional relationship with 10 points. Now, I don't know if it's linear or non-linear, so it might be flat. It probably is flat for a drag coefficient. But anyways, let me erase that just in case I goofed up here. The drag coefficient, unless you're going through some sort of transition, usually doesn't change that much, but you may find that you get some sort of relationship like that if you have CD and then Reynolds number down here. So anyways, what that is showing is that in order to do this experiment, you don't have to do 10,000 experiments like we were originally seeing. You can actually just do 10. And that's going through a little bit of analysis. It goes a long ways. And so that is really the value of the Buckingham pi approach. All of a sudden, by going through this approach, we find the important non-dimensional parameters that are governing the experiment that we're looking at. And so that is Buckingham pi. We'll take a look at another example in the next segment, and then we'll look at other aspects of dimensional analysis in fluid mechanics.